So in section 5.3, we're going to look at a few new formulas for you. So I'll show you where these can be found in your book so you can write these down. But here's kind of the main idea. If we wanted to find some values like this, right, things that are not on the unit circle, like we don't really have a value for 105 degrees, we have some values around it, but not for 105. So if we look at our unit circle real quick, there we go. So, right, we have values for 90, we have values for 120. We know 105 would be somewhere in here, but that's not one of the angles that we're typically going to look at on the unit circle. So how do we come up with values for that when it's not one of these main type of angles that we have? So we're going to take a value like 105, and we want to split it into two values that we do know, right? And so we do have values for 135 and for 30. And so we're simply going to write that as a subtraction statement. Obviously, you can see this still equals 105. By splitting it up into angles that we do know, though, is now we can apply a formula to this and then go ahead and simplify it from there. Do keep in mind that when you're doing these, there are several different ways you could write a statement that would equal 105. Okay, and so when you see something like this is just one way that you could do it. Let me go to those formulas real quick. So on page 415, looks like this. So for the cosine of a sum or difference, which is the one we're looking at right now, whether we do plus or minus, this is what it comes out looking like. So we're going to come out with four terms based on this. So we have whatever we split these this degree into. So like on the one that we're just seeing, we had 105, and we broke it into 135 and 30, right? So that makes u our 135 degrees, and v would be our 30 degrees. So we're going to write that as cosine u, cosine v, plus or minus sine u, sine v. As far as the sign in the middle goes, it's simply the opposite of whatever we have here. So if we write this as a subtraction statement, like the one that we saw in our example where it said 135 minus 30, so if we write that as a subtraction, then in the formula set up over here, we would have a plus sign. Right, so you can see that this is plus over minus, this is minus over plus. That just means we're going to have the opposite symbol here than what we do here. So anyway, so here's what they did. They said this was like our u value and this was the v value, right? And so they wrote it as cosine u, cosine v, plus sine u, sine v, right? So they just plugged in the values for what those would be. So 135 and 30, and their sine values as well. We can find those just straight out of our unit circle. So if you take the values for 135, so they're putting this in for the cosine value, they're putting this in for the sine value, since that's our y-coordinate. And for the 30 degree portion, they're using this for cosine and this for sine. And so they're just plugging those into the formulas where they would fit. And then from there, we just simplify it as much as we can, and we have our result. So we're going to try one of those so you can see how that works out. So if we had the cosine of 75, again guys, there's a couple ways you could break this up. Sometimes you will be told how to do it. Like they might say use a difference formula or use a sum formula. So they're telling you they want you to use addition or subtraction. But if they don't specifically tell you, then we can pick sort of whatever process we want. On the one that we just did up above, you'll notice on this one it didn't say, it just said find the exact value. So we could have used an addition scenario or a subtraction scenario to find it. Like you'll notice 105 is also, that could be written as 60 plus 45, right? And I could have worked with an addition formula instead. So it's just a matter of whatever you see is easiest if the directions don't specifically tell you. I know this one did say specifically to use a difference identity. But I'm using a sum instead because the one up above just showed you how to do a difference problem. I wanted you to see the other version where it's now a sum problem, and so we're going to use addition instead of subtraction on this one. So 75, so if I wanted to consider two angles that add up to 75, such as 30 and 45. So now if we throw that into the formula that I was showing you, which looks like this one. So the u, on the way I just wrote it, is going to be my 30 degrees. The v is going to be my 45 degrees. And so we're going to throw out this scenario right here. So cosine, cosine, minus sine, sine. So I'm going to see this as cosine 30 times cosine 45 minus, remember it's always the opposite of what we got right there, minus the sine 30 sine 45. And so now that we have that laid out, I can simply throw in the terms that they represent. So we're going to figure out what is the cosine of 30 and 45. So we know from our unit circle cosine 30 is our rad 3 over 2. Cosine of 45 we know is rad 2 over 2. Now we got to throw in their sine values. So sine at 30 is 1 over 2. Sine 45 is rad 2 over 2. So we're just going to do a little cleanup on that. I'm going to write it above here because I'm going to run out of space. So if I multiply those first two terms together, I'm looking at rad 6 over 4 minus, if I multiply those together, I have rad 2 over 4. Since they have a common denominator, we can combine those to look like this. Oops, it's supposed to be a 2. Keep that denominator as a 4. And so this would be the best way to write that answer. So remember, you are not allowed to add or subtract radicals that are not the same radical. So those guys cannot combine together. So that's just as simple as we can make it. All right, so we're going to jump on down here to this formula. So guys, the other thing I wanted to show you is the only formula we looked at on 415 was the cosine formula. Right, so this is just for working with cosines. Of course, we also have formulas for sine as well. So here's what the sine formula looks like. So it is a little different than the cosine formula. One thing to note on this is whatever you have as far as a plus or minus is going to match right here. So if this is positive, then this has got to be positive as well. So again, notice a little bit of a different setup for the formula when we're doing this for a sine value. So let me take you back to what they're showing you here. So on this one, they wanted us to kind of work backwards, right? They're like giving us the layout, and they wanted us to figure out sort of the original statement that this would have come from. So in other words, it's like they're giving us this statement right here, and they want us to figure out what was the original statement that it came from. So when I see sine cosine plus cosine sine, I know that fits the sine formula that I was just showing you on page 416. So I know this is going to be a sine function, and because it's plus, remember in the sine function it would also be a plus, so which means they are adding the 25 plus 5. In other words, we're looking at the sine of 30 degrees. So if we simplify that and trace it all the way back to where it started, it would have looked like this for the sine of 30. You can kind of look at these before I even flip the page, but same thing on this one. You'll notice this looks more like the cosine formula that we looked at. So it was cosine cosine plus sine sine. So on this one, remember in the cosine formula, it was the opposite symbol. So it's going to be a subtraction symbol. What are the two angles? They're pi over 4 and pi over 5. And so if I just subtract those guys, I can take this back to where it started. Let's see, we need some common denominators on those. So let's see, for 20, let's think of that as 5 pi over 20 minus 4 pi over 20, which is just 1 pi over 20. And so that would be the original angle that we would have started with. So that's all we have to do on these, is just kind of trace them back to the original form using their formulas. And let's just peek at the last one here. So again, when I see sine sine minus cosine cosine, I know this fits the cosine formula because my sines are together and my cosines are together. But the weird thing about this one is, in the cosine formula, the cosines come first, right? And then the sines come last. So on this one, I would have to do an order switch in order to arrange it to fit the formula. And then I could recognize that my angles are 3x and 5x, and then I set it up into the formula from there. So here's what that one looked like. So we already did this one on the other page. Here's one we're looking at now. So they had to factor out the negative in order to switch the order of the problem, right? And now it models after the cosine formula where the angles were 3x and 5x. Again, it's always going to be the opposite sign in the cosine formula. And so from there, we can bring it back to just the negative cosine of 8x. All right, let me bring you down to the next page. All right, so what if we said find the sine of 13 pi over 12? Of course, this is not one of the angles on our unit circle. So here's where we would have to split it up, either using a sum or a difference setup, one of those. So on this one, I've typically found that it's pretty tough oftentimes for students to deal with these when it's in radians, because the way you have to split it up and create common denominators in order to see the values from the unit circle. So usually on these ones, I would encourage you just convert it into degrees, because I think you're going to have a much easier time with it if we do that. So I'm going to do my 13 pi over 12. And let's multiply that by 180 over pi. So we're going to see this as 195 degrees. It's going to be a lot easier to add or subtract angles when we see it as an integer rather than a fraction. So we'll still get the same result, but I think it'll be easier now to work with the 195. So on this one, you have a choice. I can either add angles to get 195, or I can subtract angles to get 195. It's really just a matter of whatever you see as the easiest thing to find. So as far as angles that would add to 195 or subtract to make 195, what if we took our 225 and subtract 30? So there's one option. So I could write this as a difference formula where I'm going to do 225 minus 30 because that would equal 195. If we wanted to do it as a sum, what if we did 135 plus 60? Right, so that would be another option. So you got multiple choices on how you want to get to the answer. There's no right or wrong. It's just a matter of whichever one is easiest for you, unless the directions specifically tell you which method they want you to use. So do look for that, but otherwise it's really your choice. I'm going to go ahead and throw this in as an addition problem. So I'm going to do my 60 plus 135. So I'm going to write this as, I'm going to work down here. So I'm going to say sine of 60 plus 135. Because this is a sine function, then here is the formula I want to model this after. Right, so I'm going to do sine cosine plus or minus. In this case, it's going to be plus because we wrote this as an addition problem, plus cosine sine. So let's make sure we get the u's and the v's in the right locations. So we're going to write this as sine 60 cosine 135 plus cosine 60 times sine 135. So I'm just plugging that into our sum formula, and now we just plug in the values for these. So what's our sine at 60 degrees? We know this is rad 3 over 2. Our cosine at 135, and we're just going to go on down the list and plug these in. So just like in our 60, the sine value is rad 3 over 2, our cosine is 1/2. Do be careful that you get the signs correct on these. So if I look at 135, take you back to our unit circle here. As I take you back to 135, keep in mind that your cosine on this is negative. So they're both rad 2 over 2, but your cosine is negative. So we got to make sure we get those right. All right, so I know my cosine was negative rad 2 over 2. This was positive rad 2 over 2. And so now we can simplify these. I got a negative rad 6 over 4. Keep the sign in the middle. Over here I'm looking at rad 2 over 4. So because they're both over 4, we could combine those as a single fraction. And you could either write this as negative 6 plus rad 2 or rad 2 minus rad 6. It really doesn't matter. Either answer would be correct. So it looks good right there. Let me give you one last scenario. So of course we also have a formula for tangents. So let's peek at that on page 417. He looks a little uglier than the other two. Tangents and cotangents usually look a little tougher than the other guys. So here's our tangent formula. So on this one, notice the u and the v. So I have my first angle here and my second angle here. So we're going to do the tangent of the first angle plus the tangent of the second angle over 1 minus tangent of the first times tangent of the second. Notice the signs on this one. Whatever you have here will match here, and this will be the opposite. So if this is a plus, then this is a plus, and this is a minus. And then vice versa if we go the other way on that. So we're going to look at finding the tangent of 11 pi over 12. Again, that's not one of the angles that we would see on our unit circle. So we want to write that as a sum or difference. I just did a sum on the last one, so I'm going to try to do a difference scenario on this one. But let's take the same approach. It's definitely going to be easier if we convert this to degrees. So I'm going to multiply it by 180 over pi. So we're going to see this as 165 degrees. Definitely easier when it comes to looking for two things that would add or subtract to make that value. So we're going to see this as 165. And like I said, I did a sum problem on the last one, so I'm going to turn this one into a difference problem. So let me find two angles that subtract to make 165. So if we're looking here at our unit circle, we could do something like 210 minus 45. So that would work. So let's go with those. So I'm going to write this instead of 165, I'm going to find the tangent of 210 minus 45. Alright, so the hardest part on this one is just remembering the formula that we're plugging this into. So for our tangent one, again, we're going to do the tangent of the first one, which is 210, minus, keep our sign, tan 45. And all that is going to be over 1 plus, so here's where your sign will change. So 1 plus tangent of the first one times tangent of the second one. So there's our setup. All we got to do is plug in the numbers and simplify it. So I know the 45s are going to be our easy one because the tangent of 45 degrees is just 1. So that'll be nice and simple. It's the value of 210. That's a little bit ugly. Let me just show you. So here's our 210. So remember, tangent does y over x. And so if I did negative 1/2 divided by negative rad 3 over 2, well, in that process, the 2's would cancel, and I'm going to end up with 1 over rad 3. So we could write that as either 1 over rad 3. So I could write it this way, or, remember, if you rationalize the denominator, that could also be written as rad 3 over 3. And so typically that's the more appropriate way of writing it. So I'm going to put that in for now. So I'm going to say rad 3 over 3 minus the tangent of 45, which is just 1. On bottom, again, I'm just plugging in here. So tangent of 210, we got the rad 3 over 3 times 1. And so we always want to clean these up as much as we can. Typically, we try not to ever leave a fraction in a fraction. Right? We don't want a complex fraction. We want to simplify this as much as we can. So here's a little side work. I'm going to create common denominators right here. So see that 1 as 3 over 3 so that I can combine this into a single fraction. So I'm going to say rad 3 minus 3 over 3. So there would be my first move for the top part. On bottom, I'm going to do the same thing. This is just, right, because of the ones, this is just rad 3 over 3. I'm going to write this as 3 over 3. So that way I can add this fraction to this fraction and get 3 plus rad 3 all over 3. If you remember, whenever you're asked to do a fraction divided by a fraction, what was always the rule? You were taught to multiply by the reciprocal, right? So in other words, and I'll just show you in case you don't quite see this process, but I'm going to take my numerator, which is rad 3 minus 3 all over 3. So there's the numerator divided by the denominator. Again, I'm going to change that to multiply by the reciprocal. Which would look like this. Of course, I can cross-cancel those 3's, and I'm simply left with rad 3 minus 3 over 3 plus rad 3. Now, of course, they don't want us to leave it like that because we got that rad 3 on bottom. So if you guys remember the process here for getting rid of those, we're going to multiply by the conjugate, which we've already talked about, which is also something you guys did last year in Algebra 2. So if I multiply by that conjugate, it's going to look like this. And remember, the whole purpose of doing that is because on bottom, if my process is correct, then I'm going to be able to get rid of the radical. Right? That's the whole point of doing this. So as we've already talked about, this becomes the whole a squared minus b squared scenario. So a squared minus b squared, which is going to look like this. We are going to need to FOIL the top. So as I go through my FOIL process, see if I can squeeze this in here. And then that guy times that guy gives me minus 3. And then my middle terms, minus 9. And then my ending terms leave me with a positive 3 rad 3. So I'm going to clean that up down here. So if I combine like terms, I got my 3 rad 3 plus 3 rad 3, which is 6 rad 3. If I combine those constants, I get negative 12. And of course right here, 9 minus 3 was 6. As you reduce these, don't forget your basic rules on these. You cannot reduce unless all 3 terms reduce by the same value. So on this one, they do. Everything is can be reduced by 6. So I'm going to divide everything by 6, and that should just leave me with rad 3 minus 2. So that's the way that one would finish. We do want to simplify as far as we can, but that's it for lesson 5.3.